Hello everyone and a very good morning to all of you. Distinguished delegates, presenters and participants from SAARC member states and other regions around the globe. Ladies and gentlemen, I am very thankful to all of you for joining us in this webinar. My name is Hassan Javed. I am a research fellow, renewable energy at SAARC Energy Centre, Islam. I shall be moderating today's webinar, the aim of which is to introduce and familiarize the professionals from the SAARC member states with the advanced digital technologies, including AI, IoT, big data in the power sector. The webinar shall include presentations from distinguished speakers such as Dr. Netra Gyawali and Mr. Praveen Kumar Agarwal. I'll introduce them briefly before the start of their presentations. Dear participants, you will have the opportunity to ask questions to presenters. You may send in your questions at any time during the presentation. We will collect these and address them during the question answer session at the end of the presentation. With this, I may now invite and request Dr. Nawaz Ahmed, who is the Director of SAARC Energy Centre, for his opening remarks. Over to Dr.
Thank you very much, Mr. Hassan, for arranging this session. Hope, first of all, I'm audible before I start speaking.
Yes, sir. Go ahead, sir.
Thank you very much. Dear participants and presenters of the webinar, good morning, everyone. I'm Dr. Nawaz Ahmed, Director, SAARC Energy Centre. I welcome you all to this knowledge sharing webinar. Ladies and gentlemen, as we gather here today, our region is poised at the crossover of a transformative journey. The SAARC region is home to over 1.8 billion people with an increasing demand for electricity. However, grid infrastructure in our region faces numerous challenges, including inefficiencies, transmission losses, and reliability issues. Digital technologies offer a beacon of hope. By harnessing the benefits of digital technologies like Internet of Things, artificial intelligence, blockchain, and data analytics, we can create a more resilient, efficient, and sustainable grid ecosystem. It provides various benefits to the power sector, such as efficient use of resources and increased production and real-time monitoring. In this webinar, our expert speakers will delve into various aspects of the topic, including overview of digital technologies, potential opportunities and challenges of its deployment, artificial intelligence applications in transmission systems management. Number 4, existing applications for the digital technologies and benefits of using these technologies. Dear participants, we have an impressive lineup of speakers, including Dr. Netra Gyawali from Nepal and Mr. Praveen Kumar Agarwal from India. We hope that their insights and expertise will enrich our understanding of digital technologies and its potential use in SAARC region. In the end, I thank you all for joining this webinar. I expect this webinar to be an interactive session, so please feel free to join the discussions and express your valuable opinions. With these words, I declare the session open and wish you all a very comfortable learning and knowledge sharing experience. Now I request Mr. Hassan Javed, the coordinator of this webinar, to take us through the agenda. Over to Mr. Hassan, and thank you all again for joining us today.
Thank you very much, sir, for your kind words. And now we go on with the webinar agenda. The first presenter today's webinar is the presentation of the presentation is AI application in transmission line asset management. The presentation would be delivered by Dr. Netra Gyawali. He is already online with us, so I'll just briefly give brief profile of Dr. Netra. He is the Chief Executive Officer of Rastriya Prasan Grid Company Limited, Kathmandu, Nepal. Completed his master's and PhD in electrical engineering from Kyoto University, Japan. He has 16 years of academic experience in electric power system in capacities of assistant professor and associate professor at Institute of Engineering, TU, Nepal. As a power engineer and a researcher, he also provides expert services in many institutions in Nepal and abroad. Dr. Gyawali is actively engaged in research and innovative activities and has published many papers in renowned international journals like IEEE USA, IET UK, and IEEJ Japan. His research areas include power electronics, distributed generation, HVDC, energy storage applications. Since 2017, he is working as the Chief Executive Officer of the National Transmission Company of Nepal. So over to Dr. Netra Gyawali.
Thank you. First of all, I'd like to thank organizer to provide me the opportunity to share my opinion regarding transmission line asset management. So to start and continue my presentation, I would like to share some of my PowerPoint slides. So let me share. Okay. So is it visible? Hello?
Yes, sir, it's visible. You are audible and visible.
Okay, and am I audible enough?
Yes, sir, perfectly all right. Go ahead, sir.
Okay. Well, so in today's session, I will be discussing briefly on transmission line asset management, the scope of transmission line asset management, and the application of AI in the area of transmission line asset management. So to begin with, so let me briefly introduce what is the transmission line asset management. So by its definition, it is the systematic approach of maintaining and optimizing the performance of transmission lines within the electrical grid. That is, one of the very prominent part is the condition assessment. That is it consists of regular inspection and monitoring of components like conductor, insulator, and towers. And then there the maintenance and the refurbishment, maybe the preventive and the corrective maintenance that are basically intended for the reliable operation and to extend their lifespan. And third aspect may be the risk management. That is the identifying and the mitigation of all the operational risk. Maybe the failure and failure due to the natural hazards or failure during the operation or many more. Likewise, one of the another aspect of line asset management is it is life cycle management. So it starts beginning from the planning and then in the construction, operation maintenance, and to the disposal part. Okay, now let us explore the scope and complexity of the asset management. I already point out a few key areas of those asset management. So one of the one of the area is the transmission tower, right? It may be the steel structure or other lattice structure, or maybe the pole. And next part is the conductors, and another part is the insulator, hardwares, and not the least, it is the easement and the ROW area of the transmission lines. So now if we talk about the transmission tower itself, then it has the foundations, legs, body, cross arms, and many more, right? And all those parts, we have the drawings beginning at the beginning of the planning to the DPR and during the construction, which vendor provides, and the sub data during the manufacture, and so on. Likewise, there are the testing details, type test, routine test, hat test, and so on. And so in all areas, we have the detail of the vendor, contractors, and many more. So in each areas, we have the tons of the data, be it in the transmission towers or in the conductor or insulator. And so likewise, there are the tower fitting hardwares. Now, then another area of the asset management is the ROW and the transmission corridors. So in that corridor, we have the survey map, and the there is the cadastral map also, which includes all the details of the landowners, the forest, environment, and those the environmental studies data, what we call the IE or the EIA. And likewise, in that easement area, we have the data of the vegetation management, how to grow vegetate or those vegetation, or how to trim them or prune them. So that is to summarize that one. We have the great extent of data. The detail of data is as we require. So the extent we need for the operation maintenance of the transmission line, right? So these data are the two types. One is the static type, like the drawings or the data during the DPR stage, in the bidding stage, or during the construction supervision or management. So basically, we categorize these data as the static data. And now there are the variable data also, like the real-time data, which is associated with the condition monitoring, and so on. So when we use this dynamic data, then we have to rely on the various sensors and the other tools. Now, the challenge in the traditional asset management is all the asset management involved on the manual inspection and the periodic right? Be it or through the helicopter, or maybe through the ground inspection of those assets. Basically, one of the drawback is it is not able to predict the asset failure, right? And its prediction is not accurate enough to have the optimized operation and maintenance. Therefore, for that one, a complex large the task involves the acquisition and management of large amount of data. Then now that is the scope of the AI tools for the asset management. Now, so what is the artificial intelligence? Although I am not the expert of artificial intelligence, basically I am users. So I'll just toss the topics which are relevant to me, or to the applicable for the power engineers. So basically, there are three types of AIs, which is now we are using like narrow-based AI. They are the simple. They do the simple and specialized tasks like Siri, Cortana, and the other face recognition systems. They are narrow-based AI. Somehow, this type of AI can be categorized in the GPS prediction. Like if I give two geographical points to move, I mean to travel in traffic, then maybe there is use of some sort of the AI to get the shortest path, whether there is heavy traffic or not, so on. So this type of AI has already been used in various sectors. Now comes the generative AI. So it uses the genetic model to produce text, images, videos, right, or the 3D models or other SPL are used. So this is the now it is the mainstream AI version now, which the ChatGPT has been used as a platform. So in that platform, we can do the lots of the tasks in the scope of the text, image, videos, and the other drawings. Right. And the third type of artificial intelligence, which is yet to actually applied in real field, is artificial general intelligence. So its scope is much more than those the previous versions. So it demonstrates the intelligence across the wide range of the cognitive tasks. So that one now we are discussing the use of the artificial use of this AI, that is the generative AI, in transmission line asset management. So the AI, the essence of AI is, as we already discussed, it has the basically four components. One is the digital technology, which is the main theme of this the webinar. So it consists of lots of the sensors and communication channel to interact with the weather condition and the condition of the assets themselves, and also they communicate with human. So the digital technology is there, and there are a lot of the data. They are through the sensors or the data in the database, or data collected in the real-time data. So there is the next part is the big data and the IoT. And the other aspect is the human interface with that model. And so that that digital technology and the big data are now they are they are workable enough to the human. So there is the high level of the communication channel, that one. And finally, there is the output generation, which is applicable and usable to us. So in transmission line asset, I have discussed two types of AI. One is in the planning aspect, which is the AI. So this AI can be used in transmission line routing. As I already mentioned, asset management, it starts from early stage of the planning and to the dismantling part, disposal part. So because of that, so it optimizes all the aspects, like which equipment is to be removed, or which vendor is to be communicated, or which equipment is best suitable for capital cost, or the operation and maintenance, or which is durable enough. So all the life cycle costs can be linked to the from the planning to construction and operation to the disposal site. So therefore the first and important part is the transmission line routine. And the next part is the digital twin, which can be used in the design and prototype testing. And next is the line operation and maintenance. So basically, I will speak on these two aspects. One is the ENN and the digital twins. So how ENN is useful in finding the route. So let us see a simple example that we use currently. Now, so we can see, for example, if I am here in Kathmandu, New Baneswar, and I like to go with Hamel, then so I give 2 points, the point of origin and destination, and then you can see I can get 3 paths, right? So what is the time of those paths, what is the traffic conditions, and what is the average distance for the other one. So this is actually one miniature form of artificial intelligence which already used in the route selections. So so this may be one that narrow-based AI, which has the specific algorithm and very limited option. So the same principle can be used in transmission line routing. For example, so I have 2 stars here. So this point, this yellow star is one the beginning point, and then is the second point. Now, for example, if I have 2 substations there, and I like to connect these 2 points through transmission line, then I can use the AI algorithm. For example, I give all the necessary data like the geographical conditions, the land conditions like the number of the landslides or the landslide possibility there, the trees and the historical sites, and the government planning, whether there is the planning to construct a road nearby. So whatever the information is available up to now, I give all those data there, and I weight those data. So which one is the first priority and which is the least priority. So based upon that, we may get so this type of route through that AI. So so we can get so one of the optimum route to connect these points. So this saves a lot of time, because now so we can do the check survey. All we have to do is the check survey, because we have all the data collected for the lidars or the drones. So whatever technology we are using now. So and the next part is the digital twin. So digital twin, so as name indicates, it is a virtual representation of the physical entity that mimics their real world counterparts. That is, they are the computational tool which are created by combining the real-time data from the sensors and the Internet of Things and other sources with advanced analytic model techniques. So because of that, so all we have to do is interact with we can tease the digital counterpart, which otherwise could not be possible with the real thing. Now, so how can we create the digital twins in the transmission line? One is, as we briefly pointed out, one is the data collections. That is, we have to gather the real-time data, historical data, whatever data available. All those data, whether these originate from the planning aspect or construction aspect or vendor aspect or standard aspect, whatever data we have to collect all those data, and then based upon those data, and we have to develop the model, computational model, which best represents the physical asset. And then what we do is to integrate those linked collected data to the digital model for the real-time updates, because the difference between the the simulation model and the digital twin is that it is the dynamic part. So depending upon our needs, we can set the update the periods or update durations, and then we do the simulation and analysis in the different scenario to that digital counterpart, and then we validate and calibrate and applied for the applied with the real part. So, let us just briefly discuss what is different. Then, are we also using the computational model? Then, what is different between that digital twin and the simulation model? So, the digital twin is the real-time data integration. So, it is the continuous updated version. And next part is it has the so it can provide the comprehensive analysis. So we can run in multiple scenario, multiple options, and also we can use that model in other testing purpose also. And that real time, rather than using the static model, we can use that real time model for the life cycle management. That is what is its the actual conditions, how much load we can provide that one. As you know, we have set the transmission line loading so this is, for example, if we are using the Moose conductor, it is like say 900 amperes, or depending upon the temperature. If temperature is slightly the higher, then the rating may be somewhat say below that 900 ampere. So what we are using is pretty the static one. Now so this model can provide us for the dynamic line rating to establish or to use transmission line in its optimum condition, I mean optimum value. And next part is the predictive maintenance. Since we are using the real version, then we can see what is its actual condition. Now, how long it operates in good condition or the satisfactory condition, then what could be the next maintenance cycle. So so it is, of course, the limitation is the cost, because it is expensive. The greater the detail and the greater scope we demand from the digital twin, then so it deserves the more cost also. So for the simulation model, so it is all known what we have used or we are using. So, so this is the static model, which I would say it is the simulation model. Now, so how can you use this the DT in design, prototype, and testing? So this DT can be used in the design of physical asset, such as tower, conductor, insulator, and the hardware. For example, DT could automatically generate tower model. For example, if we give the base width, leg angle, cross arm width, and the other, the weather or the wind conditions, so all the data, and it can automatically generate tower model. Whatever inputs or whatever requirement we give, and yes, next part maybe which we do during the testing, the optimum member size. What could be the optimum member for that tower design, or what could be the redundant one? So what is the extent of redundancy we need in the tower? for the given conditions. And the next part is that can be used to predict the failure points in the tower test. Rather than we actually go for the testing, we can do that one. Of course, we cannot avoid the real test, but we can the optimize, or we can shorten, or we can value add the physical testing. And the last part and the most important is that we can avoid or we can limit the extent of destructive tests to be done, because we can play with the digital twin that we couldn't do with the physical counterpart. Now, so next the phase would be the use of digital twin in the transmission line operation and maintenance. Now, the value of the real-time data is actually in routing, operation, and maintenance of the transmission systems. Because of that one, we gain the visibility. We get the accurate visibility of load flow even at low voltage levels, right? Or in the different the generating inputs, the solars, winds. So that is, I mean, we have the real-time load flow in real-time situations of the systems or the inputs. And then we can use to identify the congested areas, and likewise the critical the part of those sections, and of course based upon those market conditions, congestions, the input and the output, and the as per the requirement of the system operator. So we can give the dynamic line routing of the rating of transmission line to the system operator. And yes, and also the impact of renewable integration. So all in the dynamic condition, right? For example, in the next 2-hour slot, what could be the real solar power integration to my grid, or in what extent I will give the load to the desired industries. So by this, as we discussed earlier, we have the detailed picture of the each and every the component. For example, so if we need the data in the level of not bolt, then it is there. If we like to know the extent of data, so what is for example, the tension during the tension on the not bolt during the construction, then we can use that data also. Or for example, during the foundation, so what are the condition of the foundations before construction? Because so it is the irreversible path. Once we establish the foundation, then we don't have the redig the foundation and see. So all those data we can they gather in the big data. So by that one, so the asset manager can optimize the maintenance schedules based upon those conditions. So so its best use is the because one of the main the objective of transmission system operator is to provide reliable service, maximum efficiencies. So in that part, the digital twin certainly help. And I like to, I don't know what is my time slot. Hello?
Yes, sir. You have still 15 minutes left.
Okay.
Please go ahead.
Now, and yes, so we can, the extend the scope, as many scopes we desire, how we can use that digital twin, for example, emergency plan. So the digital twin can provide the various emergency scenarios. So, for example, what could be the impact of the natural disasters on the critical component, or what could be the effect of the cyber attacks to the systems. So we can now expose that those events in the digital twin. So which is not possible, or which is not affordable in the real systems. And so by modeling those scenarios, the operator can visualize how the grid might be impacted, right? To develop or to design the mitigation strategies, the effective asset management. Now, I would like to point to some successful AI implementation in the various, the utilities. So these are some examples of implementation in the Galia project. So, and basically when we use those AI in our transmission systems or in our systems, so the primary data would be the LiDAR technologies and the sensors, as many sensors as available. So here the Galia has been used, that one. So its purpose is to basically for the overhead line inspections and the automations, and we have the diagnosis for regular maintenance. And the next part is I observed in European electricity in grid in the INDESOE. So they have also some plan for the digital twin implementation. And there are other examples also. And in our case, so we are software for the digital technologies, and the some software tool in asset management, which is the traditional software we are using now. We are also thinking to use and apply those AIs in transmission and asset management. So as we discussed, so the extent of using the AI is guided by the cost and our requirement. So the greater the requirement, the greater is the cost. But somehow we are gradually applying that part in our system also. So so thank you. Maybe we can use the additional time for the discussion, and I will happy to share and learn some of your concerns. Thank you.
Thank you very much, Dr. Netraji, for excellent presentation. So, ladies and gentlemen, Dr. Netra has introduced with the participants the digital model, the twin concept, the type of AI is used in design, testing of transmission lines, plus the operation and maintenance of those grid infrastructure. So how effectively AI can be used. And he also quoted some examples from the Western world whereby these different projects are being implemented or they are ongoing projects. So, Dr. Saab, we have some questions. So, I would like to address them right now, and then we can leave the rest of the questions after the second presenter is over. So, over to few questions. We have a question that the status of implementation of digital technologies in South Asian countries. Where do we stand?
Okay. I mean, our standpoint of digital twins, you mean?
Yes, implementing digital technologies in these infrastructure of power grid. How effectively have they been used in any of the SAARC countries or in our region?
I think the digital technology is already the integral part of the power system operation and asset management. So now, so we have added something more on the digital technology that which is AI. So my response would be the digital technology we have used in our system operation and the asset management. But what we are talking is the whether in what extent we are using the AI is, I think it is the limited one. So it is, I think, in early stage in SAARC region.
Okay, sir, thank you. And another question is regarding the cost associated with DTs, because you know that in our South Asian countries, normally cost drives everything. So, what is the cost associated with introducing these technologies in the power sector? And if you compare the benefits with the cost, just a brief comment from your side.
Okay, so I think it is the very the important and crucial question. Basically, the cost is associated with the extent of its use, as I mentioned 2 times. So to begin with, we can use in the lower cost model, because if we use the digital twin for if we use the update or the regular update is, let us say, once a day or once a month, then we can have the cheaper model. All we have to do is how often we have to the sense the data. For example, how often we use the drone through the transmission line or the towers. So whether we need daily basis or monthly basis or weekly basis. So another part may be, so what is the extent of the sensors, so which are the hardware, right? So some hardware are fixed with the asset themselves, some thermal sensors, some cameras. So the real cost in transmission systems in hardware part is the the frequency of the supervision or monitoring those data. And the next part, which is the operational and the data management part, is the how often we have to run the system. So what is the size of the data? So so it is guided by that one. I think the marginal cost of the AI to the benefit is not so the costlier. So if we use the limited cost, limited resources for the primitive AI model, that's fine. Now if we get the the hardware and software to meet the higher demand, then so we can, I think all we have to do is the optimize, and with the the research and the development in those area, the cost of the cost of those AI in terms of benefit would be the less.
Okay, thank you very much. So, Dr. Saab, one last question. We know that the renewable energy is getting popular in South Asian countries last 1-2 decades, and in the energy mix or the power mix, their ratio is increasing every year in all the South Asian countries. And we know the intermittent nature of renewable energy. So grid operators are always very curious about the absorption of that intermittency of renewables. Plus, on the other hand, the electric vehicles are being introduced in many South Asian countries, and we also know the cyclic charging patterns of that electric vehicles. Normally, they are charged at home during the night, so the electrical load would be increased during the night. So, how effective do you think the use of these technologies, latest technologies mentioned by you for evaluating and absorbing the power coming up from renewables and the power going towards the electric vehicles charging?
Yes, so because of that, the intermittency of the generation, which are the renewables like solar and wind, and the intermittency in the consumption pattern. So, as you mentioned in the EV, so it means that we have the higher degree of uncertainty in the both in the supply side and the load side. So it demands the AI tools to manage that uncertainties. So definitely now the AI or the in that case, to manage that case, the ANN, the software like ANN and the similar the tools would be required, and of course, I mean, without the AI and those sophisticated technology, it would be difficult to accommodate those the higher degree of uncertainties from the supply and the demand side. So I would say.
Thank you very much, Dr. Netra Saab. We will again invite you during the question answer session at the last end of our webinar. So again, grateful to you for taking out time from your busy schedule and joining us in this important webinar. Thank you very much again. So over to our next presenter. Our next presenter would be giving presentation on digital technologies in electric power sector. The presenter is Mr. P.K. Praveen Kumar Agarwal, who has served as the Director and Chief Information Security Officer of Grid Controller of India, formerly known as Power System Operations Corporation Limited. He brings forth over 43 years of experience in the power sector areas like the electricity market, grid operations, SCADA, and cyber security. He has worked on multiple projects as an advisor and consultant for international organizations such as USAID, MCC, Tetra Tech, and Innovative Wind Energy USA. His work involves participating in various international projects focusing on banks, utility, digitalization, large SCADA systems, electricity markets. He has published over 50 technical papers and articles at national and international levels, contributing chapters to books on farms and power systems, and delivered invited talks at many international and national conferences and panel sessions. We are grateful to Dr. Agarwal for joining us. Over to you, Dr.
Thank you, SAARC Energy, and thank you, Dr. Netra, is giving so good presentation on using AI for transmission asset management. So transmission asset management really a tough job for transmission, and I remember when I was in transmission system, I used to do patrolling on foot. So this really good for using AI. And so my presentation is on digital technologies in electric power sector. So I have this present already you have given my introduction. My outline of my presentation is the introduction first, and then digital technology in distribution and consumers, for consumers, transmission and operations, and renewables and DERs. So they are very high penetration of digital technology in these areas, and benefits and challenges. So start with, if you see the grid, so grid has transformed. It's transformed from the a local grid type when it started in 1881 at Pearl Street station in Pearl Street generators in Newark. So that was it started as local grid, and local at isolated and disconnected grid. And slowly then when the AC system was invented, then the grid started connected, and then different local distribution company, which were mainly municipal type of distribution company, and they started connected. So that grid 2 came in force, and this becomes an interconnected grid. And then after interconnected grid, smart grid came when this IT infrastructure and physical infrastructure of grid start merging, and they taking the advantage of automation in grid system. So I will take my full, yeah. So then now this is grid 4, which is called digital grid, and decarbonized, distributed, and digitalized. So all these 3D are they have come in application of grid, so the grid has become digital grid. And this, so world over, now policymakers, planners, engineers, they are striving to keep the grid resiliency. Resiliency is very much required at present, because so many renewables, so many variable generation, variable load, and so many inverters, power electronics, and then variability and other things. So this grid resiliency and minimizing the cost to consumers and environment friendly. So these three objectives of policymakers and planners has drive the application of digital technology in. But digitalization yet is another dimensions of cybersecurity. So digitalization has added another dimension of cybersecurity. So when these IT systems are applied in a physical system, so this becomes a cyber physical system, and then a problem of cybersecurity also has emerged, and so that is to be taken care of. So this is a very known value chain of power delivery, starting from generators, transmission, distribution, and customer. So because I have shown here, because I am going to deal technology at each level, digital technology at each level. So there are many portfolios, many type of technologies, digital or electronic or power electronic technology, which are being used across the value chain of power delivery, like generation, transmission. So there are two things: ITC network, information and telecommunication technology, and renewable and distribution generator. This has been integrated in all four components of value of power delivery value chain. And then there are many other technologies which we will be discussing in some of the technology, not all, because this time is limited here. So some of are this wide area monitoring and control, which is in generation and transmission, advanced metering infrastructure in distribution for consumers, automatic generation control in generation and transmission, EV charging infrastructure, transmission enhancement from the fax devices, outage management system, SCADA and EMS, advanced DMS. Advanced DMS is the distribution management system, the advanced version of older DMS, demand response for consumers. Dynamic line rating is a technology which is being used in transmission system to take to use use full capacity or capacity up to the thermal rating of transmission lines, pumped hydro storage, demand management. REMC, Renewable Energy Management Center, has been created, which are the special center for handling the renewable energy in the grid. Volt bar optimization, or volt having the voltage profile, managing the voltage profile, power quality management, battery, peer-to-peer trading in blockchain. So rooftop solars has come, and then rooftop solars many times the resident may not require the outcome of rooftop solar, so they can sell that power to their neighbor or to their peer, or they can inject in the grid. So there are many technologies, peer-to-peer technology, which is being implemented in India also. DER management system, distributed energy resources, they are connected to the edge of the grid. So as in means behind the meters, and then the management of there is very important, and virtual power plants. So, but there are many technologies, so I will be dealing only some selected technology which are more prevalent at present. So like if I have chosen the three groups for the technology, digital technology in distribution and consumers, which is called AMI, ADMS, GIS, distribution automation. So all automated metering infrastructure, advanced DMS, geographical information system. Customer services can be improved with digital technologies, prosumers and P2P trading. And then again in transmission, SCADA EMS is a proven technology which is being used since last many years, I think more than 20 years. But WAMS, wide area monitoring and measurement system, is the new emerging technology which is being implemented worldwide for managing the dynamics of transmission system or system transmission operation. Renewable Energy Management Center, ancillary services, AGC reserves, and then fact device for taking care of transmission system and increasing the limit of transmission loadings. Then renewables and DERs, if we see that they are the grid edge technology, which is mainly used for in the behind the meter or connection with the virtual with the power plants and virtual power plant and microgrid inverter. So let us see each technology one by one. So let us first I will deal with the distribution and consumers. So there are some technologies this which I mentioned here. So one is I will just take the pointer. Yeah. So advanced metering infrastructure. Advanced metering infrastructure is a technology which is a foundation technology for the smart grid. So the grid 3. And this is AMI is an integrated system of smart meter communication network and data management system. So it provides a real-time data on the consumption of the consumers, and also provide the remote connect and disconnect. So if there's a problem in meter or the there is a deficiency in grid, then and required some relief, so that meters can be connect and disconnect for a small time. And these benefits are for this AMI is energy auditing and reduction in commercial losses, because AT&T losses are more than the percentage of AT&T loss is more is in distribution utilities. It may be about 15 to 20% or 40, even 40%, and most of them is a pilferage of electricity by consumers or unmetered electricity. So this can be evaluated this system. Then remote detection of meter tampering. And meter tampering detection can also be done with the AMI infrastructure, and then most of the data when the data is coming to the central place, and when data analytics is done, and it reveals that which meter seems to be tampered. And then remote disconnection whenever required can be disconnected remotely and is even connected remotely also. Geographical information system is a technology, is a representation of on-field infrastructure in the computer system. So now the operator or smart grid operator, they have complete geographical information, complete current status of the assets which are in distribution sector, because distribution is assets are very widely spreaded, and so they have real-time status and real-time location of this. So this increases the situation awareness, visualization of field devices, help managing outage. So if any feeder is out, then it can be located on the computer system, and then maintenance team can be deployed immediately from a center location. And then so it reduces the restoration time of outage. Advanced distribution management system. So distribution management system is a previous technology. Now it is there is a advanced technology which is integrating SCADA, DMS, and OMS. OMS is outage management system in a single system, and then collecting data from data consolidator unit, RTUs, and GIS. So SAP is a ERP system, and this all data is being used in ADMS. So it provides a quick decision capability to the operator, reduction of technical losses. In then I have a slide of it, actual data, how much it reduces the technical losses and other restoration time. Automatic load shading can be done with this, and schedule load shading, automatic load shading, historical data for planning of analysis. Then distribution automation. Distribution automation is providing a self-healing network to the consumers or customers. So if any one feeder is out, other feeder can come in force. So it provides a self-healing network and reduces the outage or improves the efficiency of the distribution system. And when this all the data is available to the control center, to a smart grid control center, like data of GIS, data from AMI, data from ADMS, outage management, then all this data can be fed and in a customer CRM system, and then CRM system generates the whenever any failure of a meter is there, or any failure of feeder is there, then CRM system generates. CRM is a customer relation management system, which is more of customer data, and their from where they are getting feeder from, which is the meter number, and where is the location of that meter. This provides the data. So if any outage is there, those of CRM generates a ticket to the maintenance team automatically, and consumer is not required to log any power failure. So this is the advantage. An executive can view the affected area, and if any consumer calls the call center, and then he or she already knows where fault has been taken place, and what is the status of maintenance team going there. So all this data, when fed to a CRM system, provide a very highly improved customer service. Peer-to-peer trading in blockchain is, again, as I mentioned before, the rooftop solar. And now generally all consumers have become a prosumers, and they are having rooftop solars. And many a time that output of rooftop solar might not be required by the consumers, or that consumers might be going outside or for some days. So in that time, there are two options to the consumers for utilizing the output of rooftop solar. One is the net metering. So the consumers can inject that extra surplus power to the grid, then he get that credit through the net metering. And other is the selling that power to others consumers who are not and who might be requiring more power. So this if you see this in a box, and the left hand box, traditional model, everything is to be done through the utility. So this is a net metering model, and then all the power has to go to the utility or to the grid, and then it depends, and then utility do that all accounting, net metering accounting, and then gives credit to the consumers at the end of that credit period. But if P2P trading is enabled, so there is a blockchain platform where then that extra power can be sold in the power exchange, which is on the blockchain, peer-to-peer power exchange on the blockchain platform, and sold to other consumers. And here they might get more money than what they are getting through the net metering. So this is again, and in India, this UPPCL and Delhi has already done a pilot project on this, and then it was the results were very, very encouraging, and I was a part of that pilot project, a committee. And then recently, Karnataka has come out with the regulations on P2P trading, and that's being implemented in India. And worldwide, other countries have already started doing this, like Australia, US, they're already doing the P2P trading. And if that I was telling this smart grid technologies, where these are especially the digital technology. I have done a study of Tata Power Delhi Distribution Company, which is one of the three distributors in Delhi area, and it is a joint stock company with Delhi government, and it took over government company from government in 2002, and this was licensed for the north. So if you see the digitalization journey, and it started in 2012 and 22, and this is the improvement. So there much improvement has happened. If you see the AT&T losses, when it took over from the government, it was 53.1%. Now at of March 19, it has come to 7.92%. System reliability has increased from 70% to 99.57%. Transformer failure rate it was 11%, now it is 0.87%. So peak load has increased, it is not decreased, and length of network has increased. So assets and loading has increased, and street light functionality has improved from 40% to 99.2%. If you see the consumer related experience, then new connection time reduced from 51 days to 2 days. Meter replacement time from 25 days to 2.79 days. Provisional billing, defective billing, bill complaint. So this mean time to repair faults has been reduced drastically from 11 to 0.95. Call center performance, at that time call center was not there in July 2002. So it's improved, and consumer satisfaction index has come to 94%. So that in 2002, we were not measuring the consumer index. So these are the beauty of our power of digital technology, which has been used in distribution and consumer system. So now I will mention about this transmission and operation, how this digital technology are being used in transmission operation area. SCADA, EMS, BAMS, and REMC. SCADA EMS is already knows, and is a very proven technology. And if you see this, see this box on the left hand, it is a normal SCADA, traditional SCADA, or conventional SCADA, where all this is being done. But wide area monitoring and measurement system is a new technology which has been invented in 1995, but in India started applying this technology in 2009. Give me some time. I have some noise, so I will.
So, ladies and gentlemen, Mr. Praveen Kumar has some mic issue. He will be resolving it very soon. So, in the meanwhile, I will take this as an opportunity to inform you that you may ask questions to our presenters, and we will address them during the end of his presentation and after the end of his presentation in the training and question answer session. So, over to Praveen sir.
Okay. So, if you see this, SCADA EMS is a conventional technology which is being used for monitoring the transmission grid. But wide area monitoring and measurement system is the newest technology, which though invented in 1980 and then implemented in US in 1995 after 1995, and then it accelerated after the blackout of 2003 in US. But in India started in 2009 its journey. And if you compare both technologies, SCADA and EMS, and if the table shows the comparison of that two technology, if you see this data reporting in SCADA system is 4 to 10 seconds. So every 4 to 10 second field data updates in the SCADA system at central control room, and they are unsynchronized also because they are not synchronized. So the measurements at RTU, at remote terminal unit, are not being taken at the same instant. But opposite to this, you see this in the wide area WAM system, it is 40 milliseconds and they synchronized. So the data comes in wide area through the PMUs. If you see this, these are the PMUs, which is called phasor measurement units. It takes this all the PMU installed in the field are synchronized with GPS, and they are taking measurement at the same instant of time, synchronized with GPS. And this data reporting rate, which is data is coming to the central control room, it is 40 milliseconds update. And so it is capturing the dynamics of transmission grid, which was not possible with the SCADA system. And nowadays, because of so much variable generators, so much solid state electronics used in the transmission system, this dynamic monitoring dynamics is very much required. And then second thing, angle measurement was not possible with SCADA system, though in India we used some calculation to measure the angle between north and west was in HVDC back to back through SCADA, but that was not so much accurate. But with the BAMS, it is possible. So now you can monitor the load angle between the two location on transmission line, and then so you can find the loading or stress on the transmission grid. Oscillation monitoring. So oscillation was never visible. It was never visible with this SCADA system because oscillations are sub-seconds oscillation, and this frequency is generally 0.2 or 0.1 hertz. So this is possible in real. This is possible with BAMS, and then so oscillation monitoring action and to achieve the greater grid stability. Post fault analysis was. Fault analysis was not available in real time in SCADA system, so we have to bring the data, call the data from different utilities, relay flags, and then use them for monitoring, for finding the root cause analysis. But this is available in real time, and the grid operators in India, they are using very innovatively these data. Dynamic behavior visibility is available now with the BAMS, and so as I told that this started in 2009, and there was a pilot project in NRLDC, and I was the project manager of that pilot project, and slowly many pilot projects took place in every region, and now India has implemented about 4 or 5 years before a full-fledged BAM system, which is called URTDSM, which is Unified Real-Time Dynamic State Measurement. And this consists of about 700 PMUs, phasor measurement units, 32 PDC. PDC are the central control room system, which collects the data of different PMUs and do the analytics. And the others is the REMC. REMC is a specialized SCADA system and some software which has been created separately near to the main SCADA control room, which is called Renewable Energy Management Center. So this is specifically for managing the high penetration of renewable energy in Indian system. And other technology which is used in transmission system are the ancillary service and reserve. So when there much variability in Indian system in transmission grid because of variable energy, so we require different type of ancillary service and reserves. So whenever there's a change in output from RE sources, so that reserve can be deployed. So if you see that there are 3 types of if you see this frequency response in case of a contingency, and then as soon as contingency happens, is the frequency goes down and then it started recovering, and then recovery is because of this ancillary service. If you see this from this is the point of disturbance, and frequency has come down to is the lowest level, which is called frequency nadir. But here you can see the slope. And this is because of synchronous inertia availability. That's why slope has there is a slope. Otherwise, it might have fall instantly. So rate of change of frequency is less here. And then second ancillary service is a primary control. So primary control is provided through FGMO, which is local to the thermal plants, and this then it start increasing the output of thermal plant through governor operation, and then you can see the frequency has improved. And then after this frequency has improved, there is a secondary control, which is available in central control room. So here is synchronous inertia, primary control. They are local to the thermal plant, and secondary control, which is AGC, like secondary AGC, which is a software in a SCADA system which senses the frequency and gives based on the frequency based on the frequency and other thing, which is called area control error, and it gives signals to a different thermal plant to increase or decrease the output of that. And then third type of ancillary service is a tertiary dispatch. The dispatch this is a manual, and this is reserve, which is procured by system operator in day-ahead market before the real-time operation. And then if still this primary control, secondary control are not able to arrest the frequency or bring back the frequency to the original level, then tertiary dispatch is done. And there are other ancillary services, synchronized regulations, correct the short-term change in electrical imbalances, contingency reserve. These are the reserves which required whenever unexpected outage are there. Suppose there's a tripping of unit which is of 500 megawatt, then require reserve shutdown, reserve units which can be used for getting the frequency back to this black start regulation. So after blackout, generally startup power is not available. So there are some plant which can start the blackout, which can give the black start power. Flexibility reserve to integrate renewable energy, frequency regulation, voltage control, where voltage control to maintain the grid stability. So these are the other some of the ancillary service. So let us see this AGC. AGC is the technology which is very much operational in all over the world for managing the frequency or stability of the grid or reliability of the grid. So if you see, there are the 4 box. So there is a SCADA AGC server in a central control room, which is sensing frequency and megawatt flow on tie lines, and then calculating all the output, and then giving the signal to plant controller. Plant control based upon the signal it start or it increase or decrease the output of unit controller, and then the frequency of grid is managed, and then again that again is senses the hertz and megawatt. If they are within the required parameter, then it will stop sending commands to this. So this AGC is called automatic generation control, which is in India it is implemented about 7 or 8 years before. Then there's other type of technology which is used for transmission system, which is called flexible AC transmission system, and they are the not very old technology, and the the cost of transmission line and losses is difficult to encounter and building them. So it is basically it's flexible AC transmission system, the group of technology which used for increasing the capacity of current transmission, because many creating a separate infrastructure, creating an additional infrastructure or separate transmission line is costly. Then right of way, problem of right of way is there, and then recovery of investment. So it is better to increase the limit of that current transmission system, so that fax technology fax devices are used. So fax is flexible AC transmission system. So based upon and this also it provide a control of the AC flow on transmission system. Generally, uh, flow of megawatt on transmission system is not controllable. It is controlled. It is based. The flow is taken place based upon the load connected to the grid. So when there are some parallel lines, one line is overloading, then other line if has a fact, then that device can be changed, and then change the capacity of transmission lines, and the mode flow can be taken care by the transmission line. Then other is the static synchronous compensator, which is STATCOM, and they are used for dynamic compensator of static bar. So reactive for grid operation, balancing of active power, reactive power, both are required. So active power is required, is balanced through the transmission system, and reactive power is used through the is balanced through the reactive power generation, which should be local. So STATCOM, SBC, and they are used for compensation of static reactive power, so that voltage profile is maintained. So managing voltage profile and frequency are both the important parameters of this. And then thyristor control series capacitor is again a capacitor, but the value of that capacitor can be controlled through the thyristor control device. So these are some fax technology which is used for controlling the transmission system. And then renewals and DERs. And renewals and DERs is generally connected with the grid through inverters, which is called, and that's why they are called IBRs. So first let us understand what are the grid edge technology. If you see this diagram here, you see the left side, this is called the grid edge, and then right side again, this is grid edge, and left side grid is the connection between the power plant. So when this connects, the point at which the power plants are connected or wind power plants, these are called grid edge at the plant end. And then grid edge consumer end is again, if you see this residential building, commercial, and after transformer, when this distribution infrastructure is there, so this is called grid edge. So these are the technologies which are connected to the grid edge are there, which is used for managing many things or ancillary services in the grid. So inverters that converts rooftop solar or EV to grid compliant power. These are the part of grid edge. Smart meters, they are the part of grid edge technology, and then smart circuit breakers and other management system that have the control of the system appliances behind the meter. So they are the different component technologies, and some technology we have already seen that smart meters, AMI. So one of the technology is the virtual power plant. So virtual power plants is a cloud-based software system that aggregates and flexibly orchestrates the distribution energy resources. So distributed energy resources are generally connected to the behind the meter or at the very low 440 or very low voltage, or it may be a 11 kV or it may be a 6.6 kV. So they are distributed, and they are very small capacity. But then virtual power plant can aggregate all these different type of DER in a cloud-based software. And then cloud-based software can manage the different DERs, and whenever required by the grid operator, they can provide the relief or they can provide the more power. So if you see how BP work, you can see here. So when required, BPP activated home provides power stored in their batteries to the grid, and BPP activated home are compensated from the other. So some homes might be having stored battery storage. Some might not be having battery storage. So the homes which have battery storage, they can provide power through BPP to other consumers. And then microgrid is other type of grid technology, grid edge technology, which microgrid generally a group of interconnected load and DERs within the small confined area, and then it acts as a single controller entity with respect to the grid. So if you see this is the box on right hand. It is actual microgrid, is one of the office in India where utility is connected, and microgrid, every microgrid has a microgrid controller which is connected to the grid like utility, and it may have DG generators. 500 kV DG generator was there, rooftop solar, 125 kilowatt rooftop solar, and energy storage. And then it was providing power to HVAC. HVAC is air conditioning system, LED lights, PCs, and other building loads. So whenever this output of these systems are not sufficient, it can connect to the utility and take power from there. And if the load is less, and then and this output of their own generators are more, then it can provide the power to the grid. So this type microgrids are supporting the modern power grid for their different requirements. Then IBR as inverter based renewable energies, REs, and so generally all renewable energy or DERs, they are not directly connected to the grid. They are connected to the power electronics inverters. So there are two types of grid following inverters, grid forming inverters. Grid following inverters are the normal inverters which follow the grid and provides them some power. It can provide some power to the grid, and it can also consume power from the grid. And grid forming inverters are the inverters which are used for connecting microgrids to the main grid. And the IVR can provide short-term ancillary service. So rapid I and Q. So basically, one USP of this technology that this IVRs can be controlled from the remote, and if they are given command, they can quickly respond to the injection of power or injection of reactive power or active power. And they can also provide the control inertial response. So when as the penetration of renewable energy is increasing, so this inertia is depleting in the grid. So we require some synthetic inertia or control inertia. So as the number of IBRs increasing, so all IBRs jointly can be controlled through a control center or through BPP. So they can provide inertial response to the grid. So and the benefits and challenges. So benefits, we have seen that if you see the generation area, increased revenue and reduced cost with digital twins and condition monitoring. Digital twins, Dr. Netra has already been dealt with, and high reliability with automatic load control. Automatic load control is a part of thermal power plant, and so this provide, and which is controlled through AGC. So it provides whenever there is a contingency in the grid, it provides more power to the grid through governor control or through direct. Lower cost of grid integration. These are the benefits of digital technology. Benefits in transmission and system operation, improve utilization of assets, increase return on investment. So when you are able to utilize transmission and it in the more efficient way, then there will be utilization of asset, and then defer to abort capex in when current capacity of current transmission can be increased through FACT devices, then you can avoid the capex, capital investment. Reduce congestion, then again by controlling the transmission system through FACT device or HVDC. HVDC also is a FACT type device. Integrate high amount of VRE, so then lower reserves requirement by faster and more accurate dispatching. So this AGC and the FGMO is lower the requirement of reserve. High reliability through better situational awareness. Like so, BAMS wide area monitoring system is provide a very high situational awareness to the grid operator. So this can be very beneficial to the system operation. Distribution company, we have already seen that AT&C loss reduction is there from 53 to 7%. Reduced cost of automated meter reading, billing, and this are taking automatically from central place. Higher quality service, outage management, reduce outage time, reduce high cost purchase, superior customer service. I've already seen that. Reduced bill through DRs. DRs is demand response from time of use, tariff metering, faster service, advanced services to prosumers for rooftop peer-to-peer trading, integrate with the smart devices, integrate with reliability and power supply. But all this digital technology, they have challenges. Many challenges, because they are based upon the ICT, information and communication technology. So there are challenge of cyber security, and there are challenge they are provide because ICT enables the remote access to the devices. So that remote access can be used by adversary to exploit their capacity in unintentional way, in unrequired way. Risk of cyber security increases by digitization. Vendor lock-in when there is a inefficiency of interoperability. So one utility may lock with the vendor, and then there is a total cost of ownership may increase. Modern electronics are like inverters are controlled by firmware, so there may be a bugs, there may be a intentional backdoor by the manufacturer or by the adversaries. So that can be exploited anytime or when required. And tendency of over automation poses difficulty in troubleshooting out of which is generally not the automated task. So these are the certain challenges, but these challenges can be overcome with different technologies. So this is all from my side, and if I think I exceeded some 10 minutes, but still I can take some question if there.
Thank you very much, Agrawal sir, for your excellent presentation. You delved into the details of distribution, transmission, and REDERs. You have covered the AMIs, the GIS of assets on distribution side, the blockchain technologies, plus on the transmission level side, you have covered SCADA, VAMS, EMS, and then on the renewable energy and distribution energy system side, you had covered grid edge technologies, microgrids, BPP, IBR, and finally on the benefits and challenges of introducing digital technologies. So thank you very much again, sir, for your presentation. So I'll quickly move on to 1 to 3 questions. We can also get Mr. Dr. Netra online also, if you would like to respond to some of the questions. Is Dr. Netra? So over to you, Praveen Kumar sir. First question regarding this is that you have mentioned a case study of Tetra Power Distribution Delhi, in which you mentioned about a pilot project where they were able to reduce the losses significantly and increase the reliability of the system. So the question is are other utilities in India following the footstep of this utility? Because you said it's a first of the kind of project in India. And the second is that the same utility, Tata Power Distribution Delhi, is it going for implementing this pilot project on a larger scale on their system?
So there are many utilities in India which has implemented a smart grid, because the smart grid was of grid 3. And Tata Power was a forerunner in that, and BSES, Tata Power, even the government utility in Gujarat. So at present, many utilities they have implemented these types of, because the reduction of AT&T losses is a part of ARR. It is a MOU, a part of AMOU. So all the utilities, they have to reduce the AT&T loss. And at currently they have given up some targets. So these targets can only be met through a smart grid system like AMI, automated meter reading, so that because that meter are read automatically. So you know that conventionally the meter reader going and then so this finding the meter is not working, so is a bit difficult. But now it is find in real time. So Tata has done. These are not the pilot project. This was the actual project. I was mentioning this, and they are integrating all these different different technologies in a single control room manner. So initially they implemented in an isolated way, like GIS was separate and AMI was separate, and then they had a very integrated plan so that they can integrate all the technology in a single system, and then they can one data can be utilized in other system.
Okay, thank you very much. Ladies and gentlemen, just for the information of the participants, the complete presentations of the presenters will be uploaded on our website. And secondly, we would also request Agarwal Saab if you could share any relevant text or any content relevant to this case study or any other material you would like to share with the audiences which is relevant to the webinar. We would like to upload them on our website. So second question is, Netra Saab can also respond on that one. Cyber security, how to ensure it, and has there been any recent accidents on the global side? People, utilities are very anxious about this aspect of digital technology.
Yeah, because digital technology is
Yes, you may
Dr.
go ahead, Parveen Saab. Then we will take a point of view of Dr. Netra.
Okay, so digital technology, because this is basically digital technology is the application of ICT, information and communication technology. So it brings that risk of cyber security. But no, there are incidents. There are many incidents. Sometimes those incidents are detected as cyber incidents, or sometimes it is not detected as cyber incidents. But technologies are available, like Grid Controller of India. They have implemented a security operation center. So how fast you detect any cyber attack? So one thing is clear, that cyber attack is bound to happen. There are bad people also, there are good people also. So bad people always trying to, or hackers always trying to attack or trying to penetrate our routers, and so internet facing routers on they are trying to attack this. But if we can respond, if we can detect fast, respond fast, and we have plan for incidents response, then this action can be taken timely, and it can be, that attack can be barred off. So like in India, grid controller has already implemented a security operation center, which is being monitored full time, and logs from different from different SCADA system under the grid controller. They are coming to the central place. They are being analyzed in real time, and their alerts are being issued. If any alert is there, then they are taking action. So there are different technology, and ISO 27001 is a basic thing. If you implement, then you have the many policies and many test or many control for averting the cyber secured, cyber-related attacks.
Thank you, sir. Over to Dr. Netra. Sir, you are not audible.
I think I am in line with Mr. Agrawal version because with the extent of using digital technology and the information technology, so the system are bound to have the cyber vulnerability. They are exposed. However, we can have the countermeasure also to how to encrypt those the attack, or how to respond them. For example, we are using the debit card and credit card. So now the use of those cards, those the money transaction are there, and their vulnerability of the the cyber theft is there. But the technology is continuously improving, and the evolution is there. So I think we have to go side by side. So this is my comment.
Thank you very much, sir. So we have a question regarding this India. Maybe Dr. Agarwal could say a few words. In P2P trading, how prices are determined in India?
The P2P trading is done through a platform which is called a provided by the service provider or blockchain provider, and they have some algorithm. So that algorithm decided match the price because in that platform, the consumer which want to sell its power, they are also bidding and giving some rates, and the consumers who want to purchase the power, they are also quoting the rates. And then that application, that digital application is matches the price of both. And if their price are matches, because there are some taker, there are some giver, and the price are matches, then that transaction clears. So like this is being. So there's an algorithm is there.
Okay, thank you very much, sir. So over to the next question. I don't know, maybe Agarwal Saab can put in some comment on that one. So these microgrids, are they installed on the feeders level or the transformer levels? What are the levels of installing this?
Microgrid can be installed at any level. It may be a community grid, like I shown the example of an office, of a big office where they are having rooftop solar, they are having DG sets, and then they are having loads, AC loads. So that can also act as a microgrid. So only this, you have to need a controller, so that all different type of resource source from the grid, source from the DG set, source from the rooftop source. That controller is scheduling, which source we will use. So it may be office level, it may be a farmer level, it may be a community level, it may be even a city level. If it's a big city, and that city like we have colonies, many colonies which they are having many number of people. So even that level can also be done. So it can be at any level. If it can be at house level also. So if you see this rooftop solar and grid supply, and if you are putting battery and DG sets, then you can also create a microgrid.
Yes. And the last point you mentioned is very relevant because one of the member states of SAARC region, Maldives, it does have different type of distributed systems on different islands. So could that micro technology be used in that case also?
Because Maldives is Ireland, so definitely they might be having a separate. But now on the problem is how to connect that, how to connect different islands. So generally islands are connected to the HVDC undersea cable, because AC cables cannot be run more than 10 to 15 kilometers. So they might be connected with HVDC system. But again, then you have to see the financial burden or capital cost, because cost of HVDC is very, very high. Terminals, cost of HVDC terminals are high. So this technology is there to connect different Ireland. But only we have to see the feasibility. We have to see the feasibility of that project. If it is really important, really useful connecting the different islands. Like with Sri Lanka, there is a agreement connecting with Sri Lanka and India through HVDC undersea cable. So again, because there may be the DPR has come and it will be beneficial for both countries. That's why they are going for this. So technology available, only financially you have to see.
Thank you very much, Agarwal Sahab. So I think we are over with the question answer session. We don't have any other. Otherwise, if participants would like to ask questions, they can also refer to us later on. After completion of this webinar, we will address them to the experts, and then we will get back to the specific question. And it's time for closing the webinar. So we had some excellent presentations by the two respected experts, and we are very grateful to Dr. Netra Gyawali, all over from Nepal, and Mr. Praveen Kumar Agarwal from India for agreeing to participate and for contributing in the Greater SAARC regions initiatives. And we would also like to invite you more on topics of these webinars in future also. Plus, on the participant side, we would also like to ask them to suggest us if you require webinars on any knowledge sharing topic, and we will like to address them in future. Secondly, the presentations of the webinar plus the concept paper agenda and the recording will be available on our website after the completion of this webinar in a 1-2 day time. You can get back to us with your suggestions and comments. So with this, if there is anything from Dr. Netra Saab, Praveen Saab, finally, or should we go for the closure?
I think so. I'd like to thank you again to have a very good discussion, and maybe we'll go on this type of discussion in the future also. So thank you.
Thank you very much, sir.
Good day.
So
Good day
thank
to
you
you, sir.
from my side also. Thank you very much for inviting and then sharing these presentations. I will share the presentation to you.
It's our pleasure. Thank you, sir, and looking forward to see you next time. So it's over from us, sir. Thank you very much. Bye-bye.
Bye-bye.
Bye. Thank you.